Welcome back to BAPSI. So we can go to a next section. So the first question is, what will be the reading in the voltmeter and ammeter of the circuit shown? Okay, here you can see a circuit and options are given, and we have to find the voltage and the current which is passing through this voltmeter and the ammeter. Okay, actually we can redraw the circuit into another structure. See, this can be the source, okay, then this can be the meter. Okay, I am changing the voltmeter to the left side, okay, and actually the voltmeter is placed across the capacitor and the inductor, and the capacitor and the inductor are in a series. So I am connecting like this, and this is the inductor, and the upper side is the capacitor, and this is the inductor. They are in series. Actually Xc is the impedance, that means the resistance offered by the capacitor is 4 ohm, and the resistance offered by the inductor is 4 ohm. So actually we see the difference between Xc and XL. Xc and XL is equal to 0. So the voltage drop by Xc is just opposite the voltage drop by XL. Okay, so they are just opposite. So the net effect voltage drop across these instruments is 0. If we are placing the voltmeter only across this Xc, okay, it will be minus 90 or plus 90, and if we are placing the voltmeter across only XL, it can be also minus 90 or plus 90, okay, whatever it is, but the total sum is always 0 because Xc minus XL is 0. So voltage is 0, voltage drop is 0. And what will be the current? So the total resistance in here, what is the total resistance in here? The total resistance in here, 4 plus 4 is 8. Actually we do not want to bother about this Xc and XL. Here we can see another resistance which is 45 ohm. Okay, 90 by 45 is the current, which is 2 ampere. So the current is 2 ampere and the voltage drop is 0 volt. Okay, because we measure the current through here, so the same current is passing through the resistor also. So the voltage drop across these inductors are 0 and the total current is 2 ampere. Okay, so we can move to the next question. Okay, second question is, most of the cases it is conceptual, and LC oscillations are similar and analogous to the mechanical oscillation of a block attached to a spring. In block attached to a spring, F is equal to minus Kx. Okay, it is a retarding force, and the electrical equivalent of the force constant of the spring is, so an electrical equivalent will be there for the force in here, force constant K. See, what is the force experienced in the capacitor or inductor? Okay, we know that the force is inversely proportional to 1 by LC, and if you are taking the inductor as a constant, so the C will be act as a force constant K. So inverse of capacitance, not capacitive reactance. Inverse of capacitor is the answer. So when we check the options, it is reciprocal of capacitive reactance. It is not related to capacitive reactance. It is just related to capacitance. So inverse of capacitance should be taken. So the second, the answer for the second question is reciprocal of capacitance. Option C is the correct answer. So we can move to the next question. Third question is, in an oscillating LC circuit, L is 3 millihenry and C is 2.7 microfarad at t is equal to 0. The charge on the capacitor is 0 when t is equal to 0, okay, and the current is 2 ampere. The maximum charge, that means the inductor and the capacitor is getting the charge and the inductor start to produce the magnetic field and the capacitor start to store the charge. Okay. The maximum charge that will appear on the capacitor will be, so that we have to calculate the Q naught, maximum charge. So what happens if we charge? The inductor gets an electric current, so it will store an electricity charge that is half Li naught square, half Li square, and what is the total charge stored in a capacitor? Half Q naught square by C. Okay, half Li square is the charge stored, energy stored in the inductor, and the energy in the capacitor is half Q naught square by L. Both are equal. Okay, when the capacitor get fully charged. Okay, so half Li square is equal to half Q. We can cut these half quantities, and Li naught square is equal to Q naught square by C. So what is Q naught square? It is LC I naught square. So what is Q? Q is nothing but I naught into root LC. What is I here? I is 2 ampere. So 2 into root of, what is L in here? L is 3 millihenry. That means 3 into 10 raised to minus 3 Henry. And what is C? 2.7 microfarad. 2.7 into 10 raised to minus 6. 2.7 into 10 raised to minus 6 microfarad. Okay. So 2.7 into 3. What the value? 60 and 21, which is 81. 2 into 8.1 into 10 raised to minus 9, which is equal to 2 into root 0.81. 0.81 into 10 raised to minus 8. Okay. The root of 0.81 is 0.9. So 2 into 0.9 is 1.8 into 10 root of 10 raised to minus 8 is 10 raised to minus 4. So 1.8 into 10 raised to minus 4. We can check our answer with the options. So 1.8 into 10 raised to minus 4. 1.8 into 10 raised to minus 4. 18 into 10 raised to minus 5 is there. So 1.8 into 10 raised to minus 4. So option B is the correct answer. Okay. See, the option has a resemblance with the first option, 1.8 into 10 raised to minus 5, but the power is different. Our answer is 1.7 into 1.8 into 10 raised to minus 4, but the first option is 10 raised to minus 5. But in second option also it is 10 raised to minus 5, but it is 18. Okay, 18 into 10 raised to minus 5. This can be rewrite as 1.8 into 10 raised to minus 4, which is our answer. Okay. So we can move to our next question. Okay. Which operation does the circuit represent? Input is there and output is there. So yes, I put A and B as input, and the first gate is not AND gate, and the second gate is also not AND. So what is mean by not AND? Okay, not AND means what? Just multiply and give a bar on the top. So AB bar is the not AND, NAND gate. NAND gate is connected as the input of NAND gate. So NAND into NAND all bar. Okay. So by using laws we can change these to AB plus AB, which is equal to AB. That means AND gate. So option B is the correct answer. Then we can move to the second question, fifth question. Identify the incorrect statement. Okay, 4 statements are there. We want to identify the incorrect statement, but one statement is the 3 statement is correct. So first of all, we need to find which are these three correct statements. Okay. First option. When a PN junction diode is forward biased, the width of the depletion region decreases. Yes, when it is in the forward bias, the width of the depletion region coming more thinner. Okay. And the B, when a PN junction diode is reverse biased, that means P side is connected with the negative part of a battery. So they are in opposite. Okay, the force increase, the repulsive force result a repulsive force, that force will increase. That means the center part, the depletion region get wider, that means get increased. So the second option is also correct. And the third option, a photon diode is operated in the reverse bias. Yes, when it acted in the reverse bias and it will eject photons, that photons is the light. It can be seen our eyes or not, that is not a matter. The photon can be in any wavelength. Okay, some of the wavelength only visible by our eyes, like UV rays and infrared can be seen by our eyes. Okay, and the fourth option is an LED is a lightly doped. Who said that? LED is highly doped. Okay, light emitting diode. It's a combination of PN junction. Okay. Okay, so the option D is the correct answer. That means option D is the incorrect statement. Okay. So we can move to the sixth question. Okay. Sixth question, 3 photodiode T1, D2, D3 are made of semiconductors having band gap of 2.5 electron volt. That means energy is given for the D1 as 2.5 electron volt and the D2 is 2 electron volt and the D3 is 3 electron volt. Okay, these are the value of energy of each diode. Okay. And which one will be able to detect light of wavelength 600 nanometer? Okay. So we can calculate separate energy for D1, D2 and D3, and this energy, that means energy of the incident wave should be greater than the energy of the band gap. Okay, that means the energy band, the gap between that gap of that band, that means energy band, the energy of this energy band should be less than this 600 nanometer. Okay, energy of 600 nanometer. So for our simplicity, we can calculate the energy of 600 nanometer wave. E is equal to h nu. So what is h? H is the Planck's constant, 6.626 into 10 raised to minus 34, and nu is equal to what? C by lambda. And what is C? 3 into 10 raised to 8. And what is lambda in here? In here the lambda is 600 nanometer, which is equal to 6 into 10 raised to minus 7 meter. Nanometer means 10 raised to minus 9. Okay, angstrom means 10 raised to minus 8. So 10 raised to minus 9 into 100 is 10 raised to minus 7. So 6 into 10 raised to minus 7 meter is the wavelength lambda. So E is equal to h is given, h is 6.626 into 10 raised to minus 34. Okay, and nu is C by lambda is multiplied by 3 into 10 raised to 8 divided by lambda is 6 into 10 raised to minus 7. Okay, so which is, we can cancel that 6.626 by 6. So approximately the energy is 3 into 10 raised to 10 to the power minus, say 7 can be go to the upside. So the total 10 to the power 15 minus 34 is nothing but 19, minus 19. Energy is 3 into 10 raised to minus 19 joule, that is divided by 1.6 into 10 raised to minus 19, the charge coulomb. Okay, so the answer is approximately 2 into 10 raised to, okay, there is not need of 10 raised to 2. The energy is approximately 2 electron volt. Okay, so which energy? Okay, the D2 energy of the diode 2 is coincide with our energy, but in general case, we want to say that the energy of the incident wave should be greater than the band gap. So, D2 is the only satisfying 2 electron volt because our energy of the D1 is 2.5. So, our energy of our wave is less than the 2.5 electron volt, and it is also less than 3 electron volt because our desired energy is 2 electron volt and it is only satisfied by the second diode 2 electron volt. Okay. So, we can move to the next question. Okay, 7th question. In figure, the charge on the capacitor is plotted against potential difference. That means in the y axis it is given as charge and the x axis it is given that potential difference V. Okay. The capacitance and energy, they are asked to find the capacitance and energy of the capacitor. Okay. So, what is the capacitance? Q is equal to CV. So, C is equal to Q by V and Q and V is given. Okay. And the energy of the capacitor is equal to half CV square. Okay. And C is Q by V. So, half C is Q by V into V square, which is half QV. Okay. And C is equal to Q by V and energy is equal to half QV. Okay. These are the two equations. So, for 10 volt of potential difference, there is a 120 microcoulomb of charge. Okay. Substitute C is equal to Q is 120 microcoulomb. So, 120 into 10 raised to minus 6 microcoulomb divided by potential is 10. So, capacitance is 12 microfarad. Okay. So, 12 microfarad is option A and option B has the capacitance as the 12 microfarad. So, we need to find the energy of this capacitor, that E is equal to half QV, half Q is what is the Q? 120 microcoulomb and what is V? 10 volt into 10. So, 120 by 2 is 60, 60 into 10 is 600 micro, the unit of energy is joule, microjoule. Okay, 600 microjoule is with option B. So, option A is the incorrect option. So, option B is the correct one. So, we can move to the 8th question. A wire of resistance 3 ohm is stretched, okay, not the point, stretched to twice its original length, that means 2 times the resistance of the new wire. We know that R is proportional to L square when we are doing gentle stretching. Okay, I already told you how to derive R is proportional to L square. Now, we have to only substitute the values. L is getting double. So, R1 by R2 is equal to L1 by L2 the whole square, and L1 we do not know what is L1, but L2 is 2 times of L1. So, L1 by 2 L1 and L1 get cancelled and the square is 1 by 4. R1 by R2 is equal to 1 by 4. So, R2 is equal to 4 R1, which is equal to 4 into R1. R1 is nothing but 3 ohm. So, 4 into 3, which is equal to 12 ohm. Okay. So, R2 is equal to 12 ohm. We can check our options. Option D is 12 ohm. So, option D is the correct answer. Then we can move to the next question, the 9th question. Okay. A copper wire of length 1 meter. Okay. The length is L is 1 meter and area is 5 into 10 raised to minus 7 meter square. Okay. Carries a current of 1 ampere. I is equal to 1 ampere, assuming that there are 8 into 10 raised to 28. So, N is equal to 8 into 10 raised to 28 free electrons per meter cube. That means that number of electrons in unit volume in copper. Okay, how long will an electron take to drift from one end of the wire to the other end? That means in a 1 meter of wire, actually this much of time is required for an electron to travel from this position to this position in a 1 meter length of wire. Okay, actually we want to find how much time. Okay, so we know that electron has velocity. That velocity is called drift velocity. Okay, put that in here, there, drift velocity, and we have to find the time. Okay, we have speed and we have to find the time. So which equation? Velocity is equal to distance by time. Okay, so we have to find the time. So time is equal to distance by velocity. Okay, distance is nothing but 1 meter, that is given inside the question, because the length is 1 meter. So the distance is 1 meter. So the time is equal to 1 divided by drift velocity Vd. So actually what is Vd? What is the equation for Vd? So equation for Vd, drift velocity, is nothing but I by NEA. N is the number of charge. Okay, number of charge in unit volume, and E is the value of the charge. Okay, and A is the current, and A is the area of the wire which have a cross section. Okay, there is a cross section is there. If this is a wire, it has a cross section, and we have to calculate the area, and area is given, and I is the current. So drift velocity Vd is by substituting to this earlier equation. So time which is equal to NEA by I, just reciprocaling these quantities, and I is 1 ampere which is given. So T is equal to NEA. Okay, substituting the values, T is equal to N is given, and N is 8 into 10 raised to 28, 8 into 10 raised to 28, and the charge is 1.6 into 10 raised to minus 19 coulomb, and the area is 5 into 10 raised to minus 7. 5 into 10 raised to minus 7. Okay, so minus 19 minus 7, which is minus 26. 28 minus 26 is 2. So 8 into 5 is 40. 40 into 1.6 into 10 raised to 2. So 4 into 1.6, we can take the 10 to this side, so it will be 16. 4 into 16 is 64. 64 into 10 raised to 2. Okay, now we can compare our answer 64 into 10 raised to 2 with our options. So no options there is with 10 raised to 2. All options have 10 raised to 3. So we need to change our answer to 10 raised to 3. That will be equal to 6.4 into 10 raised to 3. Okay, now we can compare our answer. 6.4 into 10 raised to 3 is the option D. Option D has 6.4 into 10 raised to 3 seconds. Actually, see, 6,400 seconds will take to travel by a electron from one side to another side of 1 meter length of wire. Okay, here we have the density for that particular wire, 6,400 seconds. That is approximately 640 by 10 minute. 100 minute. 100 minute means approximately 1.45 of hours to take by the electron to travel from one side to the another side. It is an approximated value. Okay, accurately we can say that 6,400 seconds to take the electron from traveling from one position to the another position, edge point of this wire, 1 meter length wire. Okay, so bye.